we are going to revisit a problem that we looked at back in Chapter 5 now that we have more information from Chapter 7 and Chapter 9. Particularly, we want to look at the meaning of the p-value in more depth. So here's the problem. Do most teens recycle? To find out, an AP Statistics class asked a simple random sample of 100 students at their large high school whether they regularly recycle. In the sample, 55 students said that they recycle. Is this convincing evidence that more than half of the students at the school would say they regularly recycle? Then we'll stop there. So we're trying to find out if more than half of the students recycle. If we're trying to find out, that's going to be our alternate hypothesis. Our null hypothesis is just going to be that the proportion of students who recycle is just 50%. So P equals the population proportion of students who recycle, and we'll say regularly recycle, but who recycle at this high school. Okay, so here's our p-hat, our p-value for the null hypothesis, our p-naught. Okay, so that's our, remember, that's the p-naught value. The alternate hypothesis is that more than 50% recycle. So we're going to say p greater than 0.5. Now, our evidence we have so far is one sample where the proportion is 0.55, 55 out of 100. So the question is 55% enough evidence? Is that far enough away from 50% for us to say that the alternate hypothesis is true? Well, you know enough to know by now that samples vary from one another, and we need to have some basis of comparison. So to do this, we made what is called a sampling distribution. This is a graph of 200 simple random samples of 100 students from a population in which the true proportion who recycle is 50%. So we set this up and say, here's our null hypothesis. 50% of students recycle. If this is true, and we always center our hypothetical population at the null hypothesis value, so if this is true, how likely is it to get a p-hat of 0.55 or above? So remember, this is called a sampling distribution of the sample proportion. So we talked about these in Chapter 7. This is why we make a sampling distribution. The whole point of a sampling distribution is so we have enough information about a single sample proportion or mean or whatever it is that we're measuring to know how, if that behavior of that particular sample is unusual. We have to have something to compare it to. So we make the sampling distribution. Now, we don't make a sampling distribution by literally taking 200 simple random samples of 100 students. We do this using a simulation. Okay, so this is a simulation that we have created. If we were to do more and more and more of these, if we did more and more samples in the simulation, this is going to turn into a nice looking, pretty normal model type of a curve. Right now it's kind of jaggedy because we only have 200 simple random samples. But we can clearly see that the 55% is not all that unusual. As a matter of fact, there are 43 p-hats that are greater than or equal to 0.55. So 43 out of 200. So we can say 43 out of 200 p-hats are greater than or equal to 0.55. That's not unusual. That's 21.5% of them. Greater than 0.55, greater than or equal to 0.55. So this would be our random chance explanation. So this is what happens just by random chance. So if we're looking at how likely is this to occur just by random chance, say pretty likely. This, getting a sample of 55% is not enough to convince me that my null hypothesis is wrong. This could happen pretty often just by random chance. this is a p-value. This is kind of an estimated p-value, but this is a p-value, this 21.5%, telling us how likely this sample or something more extreme is to occur if the null hypothesis is really true. Okay, so let's take a look at, so I am not convinced that p equals 0.5 is false. Okay, I can't be convinced that it's true, but I certainly am not convinced that it's false. Okay, so let's look at the second sample. Now we have a p hat equal to 63 out of 100, or 0.63. So when we look up at our graph, that only happened one time. Okay, so this is 1 out of 200. This is a very unusual occurrence. So the p-value here is equal to 1 out of 200, and I'm going to say the approximate p-value because remember this is just based on a simulation of 200. It's not based on the whole normal model, or about 0.05. Now I'm going to show you that there's actually a way to calculate this using the normal model. So on my calculator I have a stat test that I can go to, a 1 proportion z test, and I can put in my p naught, my null hypothesis value of 0.5. I can put in my number of successes, 63 out of 100, and I can put in my alternate, which is a greater than p naught alternate hypothesis, and notice I get a p-value of 0.00466, which is pretty close to 0.005. And actually I think I put 0.05, but it should have been 0.005 on the paper for 1 out of 200. 1 out of 200. 1 out of 20 is 0.05, so this is 0.005. So the p-value from the calculator, from the 1 proportion z test, and we'll learn how to calculate this later, is this actual value. So if I were to interpret the p-value, how would I interpret this? Remember that it is a conditional probability. Symbolically, I could say that the p-value is equal to the probability that p hat is greater than or equal to 0.63 given that p is equal to 0.5. So in words I can say if the true, and I think I'm going to type this because I can write it more neatly and a little more quickly this way. If the true, let's make this bigger so you can read it. If the true population proportion of students who regularly recycle, that is really hard to say fast, is 50%, the probability, I'm always having trouble spelling that, of getting a random sample of 63 out of 100 students who recycle or more. Let's see, I'm going to put the or more back here because I think it sounds better in the sentence. Or more, and that's important. And I'm going to underline that because that, remember, it has to be an area under the curve, so we have to have 63 out of 100 or more who recycle is only 0.0045. Okay, so this is interpreting the p-value. If the true population proportion of students who recycle is 50%, the probability of getting a random sample of 63 out of 100 students or more who recycle is only 0.0045. Now, that's what the p-value means. Now, the question is this enough evidence is this convincing evidence that more than half of the students would say they recycle? So this is called making a decision with the p-value. So this is interpreting the p-value, okay, symbolically and in words. This now making a decision with the p-value. When we make a decision with the p-value, we want to always compare it to some significance level, alpha. So let's say alpha is equal to 0.5, or 0.05, sorry, 0.05, 5%. What we do is we compare the p to alpha. We say since our p-value of 0.0045 is less than alpha equals 0.05, we have convincing evidence to reject. Actually, I'm going to rewrite that, sorry. We reject the null hypothesis. And you can just write we reject HO. Now, notice there's no context in here yet. We're going to include the context in the next sentence. So this is a decision. Okay, we compare the p to our significance level. We say if it's anything less than 5%, we're going to say that's unusual enough to reject the null hypothesis. We have convincing evidence that, and this is our evidence about the population, remember, we're testing, making it, testing a claim about the population. We have convincing evidence that the true proportion, or the population proportion, the true proportion of students at this high school who regularly recycle is really greater than 50%. Greater than 50%. Or we could say we have convincing evidence that the true proportion who regularly recycle, or that the majority of the students regularly recycle, because that's what the question was asking. So this is interpreting the p-value, this is making a decision with the p-value, and the decision follows directly from the meaning of the p-value. We're saying this is an unusual occurrence given our hypothesized population. Since it's unusual, we're going to say our hypothesized population is probably not correct. Now we're going to, this is kind of the big new idea. Then we're going to combine this together with the 4-step process for doing a hypothesis test or a test of significance, and see how this, and this is really the conclusion part. Okay, so we've done our beginning part, which is writing our hypotheses and stating our parameter. We've done our ending part, which is writing the conclusion. The middle part is not much different than what we did with confidence intervals.